Yeah, I think the live stream is on.
Okay, the only thing is when you leave, what you have to do is to first, I think you should be able to end the live stream now that I made your co-host, no?
Yeah, I think so. Let me see.
When you click on the more button,
I don't see any more button there. I don't know if I'm looking at the wrong place.
that's okay then.
I think if I end the meeting, the live stream should end automatically, right?
No. That's the problem. You have to
Okay.
end the live stream before you end the meeting. Otherwise, so what I will do is I'll also start recording. Okay.
Okay. Yeah.
Can one of you, Paramala and Ratnakar, check if Amin is joining today?
Yeah, we'll text him.
Yeah. Yeah, maybe you should start. Okay.
Okay. Yeah, sure. So I'll start. Yeah. So let me start the screen share first. Also, give me 1 second. Get the Wacom tablet.
Yeah, but if you have to end it, you stop the recording before you end. Yeah.
Yeah. So let me check if I can at least do that. I don't know if.
You don't even see the stop recording button?
No. So I think I'll have to record it on my end for that to work.
Oh.
Yeah. So maybe you stop the recording and then I'll start recording on my end.
Okay, so then you can try that.
Yeah. So
So this is like a backup. Okay.
Yeah. Sure.
Yeah.
So I'll record on my.
Okay, now I think you're
Yeah.
stuck.
Now I can stop. Yeah. Sure. So now
In the worst case.
Yeah, in the worst case, we at least have this recording, and I'll upload this to somewhere. Yeah, I'll make a drive folder, something like that.
So why don't you share the screen?
Yeah. So give me 1 second. I'll just prepare the Wacom tablet because, yeah, I'll start the screen share. So is someone else, like anyone else, joining in, or?
Oh, there are only 2 people.
So yeah, I think we can start.
Amin will be joining as well.
You can wait for a couple of minutes because Amin is supposed to join.
Okay.
There are only 3 people. I usually wait, even if it means for 5 minutes. Yeah?
Yeah. Also, how long can I, so how long is everyone free for? So I've planned for like,
No. I mean, I think, see, I don't want, yes, 1.5, I mean,
yeah,
1 hour, 15 minutes is the usual, is the lecture. Okay.
right.
So 1.5 hours is the max that you can go.
Yeah, sure. So that's how I planned it.
Yeah. This is, since it's also, uh, this is a
Yeah,
special
this is
class
not
on the
a
weekend. So
usual
I
time.
think you should, yeah, end
Yeah.
it. Yeah.
So yeah, so I'll make 7 like the hard stop. 7 o'clock. That is fine with everyone, right?
Yes. I mean, yeah. So is that okay, guys?
Yes, sir. It's okay.
I appreciate your uh, uh, making a special consideration for this special session for all of you.
Okay, yeah. So I think right now everybody has joined. Yeah.
Yes.
Okay, so this yeah. So everybody has joined in. Okay. So
You join. I mean, you start. I'll be here for some time. Yeah.
yeah, sure. Yeah. So okay, so let's start this. So what we're discussing about today is something known as BDDs, or Boolean decision diagrams. So to like first understand BDDs, let's first look at some general examples of what we call normal forms, right? So a normal form is basically if you want to fix a certain canonical form in which you want to write all your propositional formulas. So that would be an example of a normal form, right? So for example, it is some set of some syntactic rules that you use to constrain yourself when you're writing the formula. So for example, I think a lot of you probably know this, the conjunctive normal form, right? So CNF formulas are basically what we say that in when we are going to say that a formula is in CNF, each formula has to be composed of some clauses which are itself uh, like going to be ANDed together, and everything inside this clause is going to be or of either a variable or not of a variable. So we have variables or their nots, and we take their ors, and then we AND such clauses together. So that's CNF. Similarly, the opposite of that would be DNF. So we have ANDs of variables or the negations, and then we take their ors, right? So these are two very common examples of normal forms. A NNF is actually like a weaker normal form where we say that, okay, we are going to only allow the negation to appear on a variable itself. So both of these are in some sense examples of NNFs. So both CNFs and DNF formulas are also NNF formulas. But for example, this is not an NNF formula because you have a not on something else. So BDDs are a normal form where we only use if then else type expressions, right? So here, for example, in CNF and DNF, we have basically, we are still using both and, or, and not, all of those operators, but we are saying that we're going to restrict where we can put them. In BDDs, what we say that, okay, we are only going to use the if then else operators. Like that's it. There is no other operators that we are going to allow in a BDD normal form. So let's first like define some notation for the if then else. So if we say that, okay, x arrow y, some expression comma some other expression, this essentially what this denotes for us is that we are going to decide based on the value of x whether we're going to take the expression y0 as the value of our formula, or the expression y1 as the value of our formula, right? So what this basically tells us is that, okay, if x is 0, then take y0, else take y1. So we can sort of fix the definition of this this operator, this if then else operator, IDE operator, in terms of our usual and, ors, and nots as this, right? So okay, so if x is 1, then pick y0, else if x is 0, then pick y1, or it can be the other way around. It really doesn't matter. So this is basically an if then else operator, and the claim is that you can like define, okay, so let's first define a normal form that basically says that we're only going to use if then else operators. So we're going to start with a variable. each one of these subterms again will start with some variable and have if then else's of them. And those subterms of those will again have if then else is of their own. So we basically nest these if then else type expressions together and we build the formula, right? So this is going to be an example of an if then else normal form. So that is an INF, an if then else normal form, where we only built the if then else operators, and we also allow constants and 1 and 0, right? Because if you want to say that, say, x is true, the way we would write that is that, okay, if x, the value of x is 1, then we take 1, else we take 0, right? So that is an expression which says that x is true. Simply not of x would be if x is 1, then 0, else 1. So we allow 1 and 0s, and we allow if then else's. And another important thing to note is that the tests are performed only on positive variables and only on variables. You cannot put something else in the if then else, like over here. We cannot put anything else other than exactly just a variable. We cannot put not of x, we cannot put x or y or anything like that. It needs to be exactly just a variable, right? So under these constraints, if you write down a formula using just the if then else operator under these constraints, what you would get is a formula in INF form. The lemma is that any Boolean expression can be expressed in INF form. So can anyone, someone quickly tell me a very brief sketch of why this would be the case? Like, that's some short intuitive proof, just to know that this is fairly clear to everyone. Hello?
The other operators and or and not can be represented in terms of...
Yeah, announce your name before you answer, because so he doesn't recognize.
I don't have the participant screen on, so go on. What's your name?
So I'm Paramalai.
So there are 3 people. One is Paramalai, Amin, and Ratnakar. Okay. Go ahead.
So what we can do is we can express and or operators in terms of this if and if then else operator. So
right.
They are already universal operators. So
so then you can always write anything. So I sort of talked about how you could do not, right? So how would you express and, for example, right, in terms of if then else? So it becomes a little difficult if you approach it in that way. So you see that
y1 to be false.
Yeah, go on.
If you set y1 to be false, then you compute x and y0, right?
Right, but then you can only AND with just a single variable, right?
Right.
Because you can't put anything else here. So this is one usual way in which we sort of say that a particular normal form is like powerful enough, is that we try to express the operators here, and we will do this sort of a similar thing for or the more refined form of INF, which we'll define in a moment, which is what are the BDDs. But another way to look at this is actually to induct on variables, right? So maybe let's look at it this way. So what we do is we take each one of those variables in some, say, predetermined order. And okay, so there's some notation which is just saying that, okay, we are going to take this variable and assign it some Boolean value, right? So if you have any expression T, you can think of that as like, if you pick one of the variables and fix it to 0, then you'll get some other expression. And if you fix that variable to 1, you'll get some other expression, right? So you have 2 expressions that you get by fixing this variable to 1 and to 0. And then the value of T is basically given by what? You can say that, okay, look at the value of X. If it is 1, take the expression where you have taken this like expression T and fixed the value of X to 1. And if it is 0, then take the expression T and fix the value of X to 0, right? And we know that, okay, so imagine if this T was in some other normal form, let's say, or just composed of AND, ORs, and NOTs. You can always fix a variable to 1 or 0 and use the various rules of Boolean propositional logic to eliminate those constants, right? And get a simpler expression. So you can, do this, simplify, and then you have 2 expressions which don't involve X. So you have X implies 2 expressions, like, or X add O, and then 2 expressions which do not involve X, right? So in some sense, you can take one variable out and decide based on that. Is this clear? And you can do this inductively over variables until you just get your constant expressions, right? So let's do an example, I guess.
Yeah, but the answer that Paramalai and Ratnakar gave is also okay, no?
Yeah. So that is okay as well. So the only thing
like what Ratnakar said was, if you set y1 to be false, then what you get is X and Y not. Okay.
Right. So the only
And then you can
problem
do the
with
negation
doing
of
that way
that
is
to get-
basically so that in that specific thing, yeah, you get OR, right? But then you can only AND a single variable at a time because you're only allowed to put in one variable over here. That's it.
Yeah, that's true. Yes.
Yeah. So that is what I basically was pointing out there. And
Okay.
yeah. So essentially, we will actually look at how we can sort of express this AND, ORs, and NOTs in terms of an if then else like structure, which is what is going to be the BDD, which I'll talk about in a few moments. But yeah, so this is sort of the proof that at least I have over here. So is this clear to everyone? Yeah. Okay. So let's just hello. I couldn't hear you.
Yeah, I said it's okay.
Okay. Yeah. So yeah, just let's go for like a quick example.
Diganta, I'm going to take off. Okay.
Okay.
Yeah. Sure.
Yeah.
So I'll keep it on my laptop, but I'll come back around 6:45 or so. So hopefully before the meeting ends. But in any case, you can leave the meeting, but unless I leave, probably it will not end. But that's okay. Yeah.
Okay. Sure. Yeah.
Thank you.
Yeah.
Bye.
Thank you. Bye. Right. So let's look at this expression here. Right. So let's firstly just fix some variable ordering. We're going to look at like pick the variable x1 first, then y1, then x2, then y2. So then, we can do this sort of recursive thing. So we have t, which is this. And then when we fix x1, we get t1 and t0, right? And then in t0, if we fix y1 to be 0, we immediately get 0. Otherwise, we get t0, 0, and so on. So what we can do is essentially, we can write down this if like INF formula in terms of a tree, right? So we can start with x1. And each solid edge would represent fixing x1 to 1. The dotted edge represents fixing x1 to 0. And then we can, go down and we have y1 then. And then again decide whether y1 is 1. If y1 is 1, then we take the solid edge. Otherwise, we take the dotted edge down to 0. So similarly, once we've decided that x1 and y1 are both 1, then we look at x2. So if x2 is 1, then we go to y2, and if y2 is also 1, we take 1. If x2 is 1 and if y2 is 0, we take 0. If x2 is 0, then y2 is 0, then we get 1. Otherwise, if y2 is 1, that is we have fixed y2 to be 1, then we take 0, right? So in this sense, we can sort of like arrange this if then else formula as a tree, right? Because you have a top level decision that you're doing. Yeah. So I think I'll use the highlighter here. So yeah, you have a top level decision that you're doing. And then, you can express this top level decision in terms of like these sub decisions as other like top level decisions for more sub decisions and so on, right? So you have a tree like structure. So in some sense, if you take the syntax tree of this recursive set of expressions, you get this tree like structure in which you like recursively do a set of decisions, and then you get to either 0 or 1. So you can write an INF formula as a Boolean decision tree, right? So it's a tree where each node or let's say each non-leaf node represents a certain decision that you take. So here, for example, the node x1 would represent us deciding on based on whether the value of x1 is 0 or 1. Similarly, once that decision is made, based on that decision, based on the value of x1, you either take the left edge or the right edge, or in our case, the dotted edge or the solid edge, right? So solid edge if it is 1, dotted edge if it is 0. So if it is 1, then we go to y1 and then we make another decision. And again, if it is 1, then we go to x2 and we make another decision. Again, if it is 1, we go to y2 and we make another decision, and so on, right? So this is in some sense a Boolean decision tree where we arrange these decisions in a tree-like structure. So note something that for each value of these variables, like each set of values that you can give to this variable, you get a unique path in this tree. and that path in some sense gives you the ultimate, like the leaf node in that path gives you the value of your final expression, right? So if you set, say, x1 to 1, then you go down here, and then you suppose set y1 to also 1, then you go down here, and then x2 is 0, and then y2 is 1, then you go down here and you finally get 0, right? And also note that sometimes we can quickly, eliminate some decisions. For example, if you know that x1 is 1 and y1 is 0, then we, looking at the formula, we know that this first clause will fail. So obviously, since there's an and here, this entire formula will be 0. So we can just directly decide that, okay, we're going to go directly to 0. So in some sense, we can also skip some decisions in somewhere, right? So this is like, basically we're taking the entire truth table and we're sort of splitting it into various regions based on the value of one variable at a time and arranging that as a tree, right? So take the value of x1, then go somewhere, then see the value of y1, then go somewhere else, and so on. And each path represents a particular value of your variables and will lead you to either 0 or 1 in terms of the leaf nodes. So here's a question. Is this, so we know that INF in some sense is a normal form, right? So we know one of the properties of a normal form is that, which we haven't proved yet, but is for INF, is that like, for a given Boolean function, the normal form itself needs to be unique up to certain constraints, right? So here's the question. Is this Boolean decision tree structure unique for a given formula?
It need not be unique, right? Because if you take a tautology, that
yeah,
every
what's come again with your
leaf will
name?
be,
I can't. I haven't
Padamalai.
identified. Yeah. Okay. Go on, Amal.
So, for example, if you take a tautology,
Right.
then every leaf node will be 1.
Yeah. Then for
But
tautology, in fact, yeah. Go on.
yeah, but there can be we can like remove some of the uh, variables in that, and still it will again be a tautology, right? So
Right. So,
it
so
can be
there's this
equivalent
one question
decision.
of, right. So there's this one question of how much redundant checks have you removed?
I'm saying for a tautological formula, there can be more than one Boolean decision tree.
Yeah. So for example, give me two things which can like represent a tautological formula.
Hello.
Yeah. So can you give me like two trees that can represent the same tautological formula? Let's say.
One of the trees can have only one variable, and it will lead to 1.
Right. So you have, okay.
Sorry, my internet connection is unstable, I think.
Okay.
Hello.
Yeah, I can hear you. Yeah, go on. So you have just one variable. Okay, I don't know why the fill is on. Sorry. Yeah, you have one variable, and then that just leads to 1 is what you're saying.
Yeah.
This is 1, right?
Yeah.
Yeah. And what give me another example?
There can be 2 variables.
Yeah, so there can be another variable here, let's say, that we sort of,
so my internet connection is kind of unstable. I'll restart my router and I'll join again.
Okay, sure.
You can let me in, right?
Yeah. I'll be able to admit you, I think. Yeah, go on.
Yeah. Okay.
Yeah.
Okay. Please
Yeah. Okay. So I'll wait for you as well. Yeah.
No, you can continue. It will take some 2 minutes.
Okay. Sure.
I have to restart.
Yeah. So okay, sure. So essentially, I mean, okay, I think I can wait for like 2 minutes. There's only 3 people. I don't know if it's a good idea to just like continue if one of us leaves. I'll give you like 1 or 2 minutes. I think that's okay. So okay. just as a like a general thing, anyone at any point, just stop me if you have any questions. I should have probably mentioned this at the beginning, right? So is everything more or less clear up until now, or do you have anything in your mind?
Yes, I think so.
Okay. Yeah. So okay, I'll maybe wait like for a few more seconds and then I'll have to start, because there are some, like it's already 5:53 as well. Yeah, okay. So I think I'll continue, and yeah. So the point that the reason that I wanted to for him to stay was because, like, so maybe someone else can also answer this. Like, okay, yeah. Hi, are you back? Hello, Aman. Yeah, maybe his internet is still not.
Yeah. I mean,
Okay. Right. So yeah, so one of the things that we can do is basically to try and to make this sort of tree unique is that, okay, we can say that we're not going to let redundant decisions happen, right? So in some sense, if you wanted to make this a tree, then this would not be the tree, right? So the tree would be like, okay, you have one variable here, and then you take a solid edge that takes you to 1, and you take a dotted edge that takes you also to 1, right? So we say that we don't allow this. Whenever we have a node which leads to the same node, both via the solid and the dotted edge, we just remove the node entirely, right? So then both of these tree would just not be allowed, and we would just be left with just one, right? So if you look at this tree, for example, here we are also taking this path directly. We're not deciding on x2 over here or y2 over here. So if we make this constraint, we say that, okay, we're not going to allow redundant decisions. So now is the tree unique? So we have added one rule, so which says that no redundant. Let me just write the rule here. No redundant. Now is the tree unique? Can anyone answer, or does anyone have yes, no, any guess? Or
I have one question.
yeah, go on.
We mean when we're talking about a tree being unique, we don't mean that one formula has only one tree, right? Because the order of the variables you take can change.
Yeah. So that is another thing that we'll need to fix. Exactly. So we what we mean is that one formula should have only one tree, and we're trying to figure out under what constraints this should be true, right? Does that make sense?
Yeah.
Correct. So you're exactly correct. So that is the second, like, sort of the second constraint that we'll have. So for a given variable ordering, we'll need to always make sure that we are always talking about a given variable ordering. So in this case, let's fix this variable ordering, right? So let's say that we are always going to decide based on x1, then x2, then y1, let's say, which is what we've taken in this tree. Y1, then x2, then y2. Correct? So if we take this variable ordering and we have fixed that we're not going to let redundant decisions happen, now is the decision tree unique?
I think so.
Yeah. It turns out that this is actually enough, right? So this will actually give us a unique decision tree. And you can sort of prove this by induction. Like you can start with, of course, just formulas over like 0 variables are unique. You can then induct over the number of variables, and you induct backward depending upon the variable order. So you start with, okay, if your formula just has y2, then it's unique. If it has y2 and x2, then assuming that it is y2 and x2, it's unique, you can add in y1 and it will be unique. And you can do that induction similar to how we like the induction structure when we prove this lemma, and you can prove that it is unique. Correct? So let's sort of look at what else we can improve about this thing. So we want to sort of, our goal here is to sort of come up with a good internal representation of a formula that we can manipulate efficiently, right? So trees are really good because we know how to manipulate the trees very efficiently in the program, inside a program, as opposed to something like a string based representation or a CNF or DNF representation of this form, right? So these are much less easily handled or manipulated in a program, right? So one step in that direction is to basically make a tree. But notice something here is that look at this part of the tree. This goes from y2 in, and we decide based on y2, and if it is if y2 is 0, then we go to 1. If y2 is 1, then we go to 0. And look at this one, right? We notice that these are isomorphic, correct? So this is exactly the same tree, in fact. So in some sense, we're storing the copies of the exact same structure multiple times. Similarly, we have this tree over here, right? Which is basically just you flip 0 and 1 over here. And you have this tree over here, which you just flip 0 and 1 over here. And these are again copies of the same structure. So in some sense, we are actually storing copies of the same structure over and over again. In fact, if you look at this entire part, this entire like subtree, you'll see that this is actually isomorphic. This is just two copies of the same subtree, right? So since we're storing copies of the same subtree, it might be an interesting idea to try and merge them. So this is what Boolean decision diagrams are, right? So you take a Boolean decision tree and try to merge various parts of the Boolean decision tree according to some rules. So we look at the rules, right? So we merge equivalent leaf nodes. That's the first step. So essentially what that means is that if we have some tree like this, and we see that there are 2 1s over here, we're going to merge those 2 1s and we're going to make them one node, and we're going to have the various arrows go to the same node, right? So we merge equivalent leaf nodes. Next, we merge isomorphic nodes in the tree, right? So this is basically what I was saying over here. So this tree, this part and this part is isomorphic. This part is isomorphic. In fact, what we can see is that this entire tree is isomorphic to this entire tree. So that's what we'll merge. So if you have some situation like this, for example, where we already have, and we can sort of imagine doing this bottom up, right? We have already merged, say, the leaf nodes, and then we merge the isomorphic trees rooted at this level. Sorry, let's take the pen. Yes, so rooted at this level, and then we merge them rooted at this level. And we can sort of do this bottom up, right? So suppose we have merged the isomorphic trees here and here. And now what we do is we say that, okay, the trees rooted at this level, this A and A, like the two trees rooted at these both of A and A, or diagrams, let's call them, these are the same. So we'll merge them, and we'll make that all incoming edges go to this merged node now. So incoming edges to here will go here, and incoming edges to here will also go here, right? So we can merge them like this. Merge nodes with the same variable and same children, essentially. And we can keep doing this over and over until we cannot do this anymore. And this is the 2 rules. And the third rule is we eliminate redundant tests, which is what I was saying over here. So we don't allow this sort of a structure to exist. So we're going to ask that if we have some decision that looks like this, if y is 0, then go to z, or if y is 1, then also go to the same z node. We just eliminate this node entirely. We just cross out this node, take all the incoming edges, and then pass them to z, right? So we take the incoming edge here and just extend it right to z, right? So what then we get is what we are going to call reduced ordered BDDs. So we have also fixed a variable ordering. So essentially 4 things here. Maybe I'll write the 4th one over here. Fix variable order. So once we've fixed these 4 things over here, what we get is what we call reduced ordered BDDs, Boolean decision diagrams, right? ROBDDs. So for short, we'll just call them just BDDs for now, correct? So let's do an exercise. Let's try to take this particular formula, and let's try to see if we can convert this decision tree into a BDD. So let's do the first step first, and let's merge all of these zeros and ones to one node, right? So this is going to get a little messy in terms of drawing, but let's just power through it and see what we get, right? So we'll have 0 and 1, and So yeah, now tell me what's going to be the upper nodes, right? So let's actually try to rewrite the tree top down, and then we'll just make all the last connections go to the various zeros and ones, right? So we have x1 going to y1. Sorry, that was a dotted one. Y1 solid to y1, then again dotted to x2, solid to yeah, so dotted to x2 and solid to 0, right? So this is a solid line that goes straight to 0. And then in this x2 we see that, okay, we go to y2, and then we take another dotted edge, and this goes to 1. So this dotted edge will go to 1 over here, and the solid edge from here again goes to y2, right? The solid edge from this y2 will go to 0, and this y2 is just the opposite, right? So the solid edge goes to 1 and the dotted edge goes to 0, correct? So similarly, what we have here is going to be from this y1, a dotted edge will go to 0, and then a solid edge goes to an x2 node, x2, sorry. And then from this x2, we'll have a dotted edge to a y2 node, and then a dotted edge from that will go to 1. A solid edge from that will go to 0. So solid edge goes to 0. And then solid edge from this x2 goes to the y2 node. And again, a dotted edge from that goes to 0. And the solid edge from that goes to 1, right? So yeah, so this is basically the structure. Let me just maybe redraw this last layer a little bit better, just so that we can look at the next merge step more clearly. Right, so from x2 we have y2 here.
You are applying the algorithm to the bottom level, right?
Yeah, so we're applying essentially this rule here, the third rule. Sorry, so the first rule. So we are applying the merge equivalent leaf nodes rule here, and that is at the bottommost level. So because that only deals with the leaf nodes, that is going to work at the bottommost level, right?
Yeah.
Yeah. And yeah, so then we have these other two y2s over here, and yeah, so this is an x2. This is dotted, this is solid, this is dotted, correct? So now let's have the two zeros and ones over here. So we have a 0 and we have a 1. And what we do is from this y2, dotted 1 goes to 1, solid 1 goes to 0. From this y2, solid 1 goes to 1 and dotted 1 goes to 0, right? From this y2, we have again a dotted 1 going to 1, solid 1 going to 0. And from this y2, we have a solid 1 going to 1, right? And the dotted 1 going to 0. So I have not made any mistakes up until this point, correct? You guys have been checking, right? Because I mean, this is very easy to sort of mess up when you're doing it by hand. And of course, we have this solid 1 going to 0 and the dotted 1 going to 1 over here. So yeah, so now in one of you, yeah.
0.
Which
From
one?
y1.
From y1, the dotted 1 goes to 0, correct? So both the solid 1 and the dotted 1 will go to 0, right? So yeah, so now can someone tell me, so let's try and apply this rule, right? The second rule, merge isomorphic nodes, and let's do it at the, say, the y2 level. So this second level, the second level from bottom. So can anyone tell me which nodes will get merged here? So essentially the rule says that, okay, look at the nodes and see if they have the same children corresponding to their dotted and solid edges, then basically just merge them, right? And of course they should, yeah, so basically if they have the same children, then they're an isomorphic node, so we just merge them, correct? So which nodes will get merged here? Will there be some nodes which get merged in any case?
So the first y2 or the third y2 are isomorphic?
Yeah, exactly. So let's just color them, maybe this one and this one, correct? Yeah. And also this one and this one, right? So when we merge them, what we get is basically, let's again redraw maybe the last two levels, or okay. So let me redraw the diagram bottom up here. Yeah, so we have 0 and 1, and then we'll have just two y2s here. So we have the green y2, which is gonna be solid edge to 0, dotted edge to 1, and we have a blue y2, which is gonna be dotted edge to 0 and solid edge to 1, right? And then let's erase this one. And let's connect up those edges, right? So okay, actually, before we do that, this x2 here, the x2 takes a dotted, okay, actually let's just redraw this, right? So sorry for sort of fumbling a little. So yeah, so this x2, what does this x2 over here? The left x2 takes a dotted edge to the blue one and a solid edge to this one. And the right x2 again takes a dotted edge to the green one, and then the solid edge to the blue one, correct? And then we have the similar structure over it. So again, so let's not rewrite the structure over it again, but we can already see that we can just merge these two x2s now, correct? So even here, we see that, okay, there's a green and a blue, and this is a dotted edge to a green and solid edge to blue. And similarly, this is dotted edge to a green and a solid edge to blue. So we can merge these two x2s. Is that correct? Is everyone following?
Yeah.
Yeah. So we can merge them, and let's just have one x2 here. So just one x2, which sends a dotted to a green and a solid to a blue. And then at the upper level, what happens is now we have two y1s, right? So again, let's shift this down a little. And let's have the two y1s here. Y1, left y1, right y1. And what we have is that the left y1 sends a solid 1 to a 0. And the right y1 sends a dotted 1 to a 0. And the left y1 sends the dotted 1 to x2, and the right y1 sends the solid 1 to x2, correct? So these two cannot be merged, right? So this is our tree up until this point. And then we have the final x1, which sends the dotted one to the left one and the solid one to the right one, right? So this is going to be our BDD for this particular diagram. And in fact, if we go to, I think, yeah, I have this in this slide. So is this BDD the same as what we had there? So move this down here. So just check that the BDD that we have sort of calculated is the same one I had on the slide, right? So the x1 sends a dotted one to this y1 and the solid one to this y1. The left y1 sends a solid to 0. The right one sends the dotted to 0, which is what we had, correct? And then the other one goes to a single x2. So the other edges go to a single x2. This x2 that sends a dotted edge to a y2, which sends a solid to a 0 and a dotted to a 1. So again, we have a dotted edge to a y2 sending a solid to a 0 and dotted to a 1. And similarly, a solid to a y2 sending a dotted to 0 and solid to 1. And so we have a solid to y2 sending a dotted to 0 and solid to 1. So yeah, we are correct. So in this sense, we can apply a rule 1 over here, and we have another rule 2 application over here. And we have a rule 2 application over here. And then we can sort of keep reducing like this for any given BDD. We can sort of use this algorithm to reduce bottom up, to reduce a decision tree to get at a BDD, right? So this is basically the definition and the intuition behind a BDD. So definition would basically be a decision tree where you have just applied these 4 rules over and over again, or bottom up, depending on how stringent you want to be in your definition. But both of them are equivalent. But you have a fixed variable order. And what you get is basically a BDD. So BDD is a decision tree, and then apply the 4 rules. So you get a BDD, correct? So this is good. So is up until this clear to everyone? Any questions? Yes, no?
When we mean isomorphic nodes, does that mean that both their outgoing edges have to be same, or incoming edges too?
No, so only the outgoing edges have to be same. So good way to think of the isomorphic nodes is this actually. In fact, I think this is actually a good point to mention this. So notice something here. So when we are actually merging these nodes here, for example, when we merge the y2s, right? So what we had done was we had merged this y2 and this y2, right? So what the nodes that we want to merge together are in some sense nodes that would have represented the same function had we taken them like out individually, right? So if you had just had this part of the tree, right, you get a like a decision tree representing some function, correct? And this part of the tree also represents the same function, right? So the intuition is that we want to merge nodes which represent the same function, so that we don't want to have two representations in our memory of the same function being carried around, right?
So I asked because it could have been possible that the x2s, two x2s on the previous level would have not been isomorphic to each other, and yet we still,
yeah, in fact, which is what happened at one level higher, right? So the y1s weren't isomorphic, so we merged up until both the y2s and x2s, right? But the y1s that we had were not isomorphic, and so we had still two copies of the y1s, right? So let's look at sort of modify this example and think about this a little. Let's say, so let's say that maybe, okay, let me erase this. So let's say that maybe you have, so this one stays the same. Let's make this a solid edge, and let's make this a dotted edge, right? So if we do this now, and let's forget about the like rest of the tree for now. So if we do this, then we still can merge the y2s, because we still know that, you know, we don't need two copies of this same like this bottom one. We don't need these two copies together. So we'll still have sort of this part of the tree will still be the same, right? So we'll still have this structure 0, 1, and we'll have only, you know, two y2 nodes here, one sending solid to 0 and dotted to 1, and one sending dotted to 0 and solid to 1, right? And now when we actually go ahead and merge the x2s, we won't be able to merge the two x2s to one node anymore. So we'll have two x2s there. So we'll have, say, something like, it's okay, I may not have some space to draw this, but let's try. Sorry. So we may have something like x2, x2, right? And then so this x2 sends a dotted edge to the dotted to 1 y2. So this is dotted here, and this sends this solid edge, and this x2 is just the opposite, right? So this sends this is a solid edge, and this is a dotted edge. So this would still be a like BDD for this sort of a situation, correct? I mean, of course, we have something above it, you know, but I'm just ignoring, I'm not drawing that part. Does this answer or clear up your doubt? Yeah. So this is basically the idea. So in fact, what we're trying to do is we're trying to make sure that we carry around exactly one representation of each sort of restricted function. So if you look at this one, this basically means, or you know, if you look at this partial tree, this is basically a function or a Boolean formula that we get after restricting some variables, right? So it's a partial assignment of our formula in some sense, correct? So we want to carry around only one copy of each such restricted subformula. And that is basically what a BDD achieves in some sense. So if you look at a BDD, each node represents one unique, like it obviously represents one formula, but what's more important is that each formula is represented by exactly one unique node, right? So for instance, in this BDD, this represents y2, right? This represents the formula y2, and this represents the formula y2 bar, correct? Or not y2. Whereas over here, we had, you know, this one representing not y2, this one representing y2, this one representing not y2, again, this one representing y2. So we had various different copies of not y2 and y2, like we had two copies of each. But why carry around two copies when we can actually sort of merge them and carry around only one? So this is the idea behind BDDs. We are trying to ensure that we have exactly one node and one node only for each sub formula that we have. So similarly, if you look at this one, what this is saying is that, okay, if x2 is 0, then so not x2 implies not y2 and x2 implies y2, right? So this is basically trying to say x2 is equivalent to y2, right? This is the formula here. And if you notice, this is also the same formula over here, right? So if you have the same, like two nodes representing the same formula, why carry around two nodes? We can do it only once, and that is what we have done over here. So this merge process is basically ensuring that each one of the sub formulas that we have represented in our decision tree is being represented by one and only one node, right? So we have only one node representing y2 implies y2 over here. And this is actually a very important point when, like, it's a very important advantage of using a BDD, right? So BDD, one of the like key points in reasons why people want to use a BDD is that you can sort of work with complicated Boolean predicates in your memory and do operations on them, which we'll see in a moment. But you're always ensured that you're not storing any redundant information, and by extension, you'd not be doing redundant calculations over and over and over again. So I want to make this point very crucial, is that we are trying to basically, we have this property where by doing the merges, this gives us this property that there is one unique node per formula or per sub formula or per partial assignment maybe, and vice versa. Right? So this is actually a very interesting like property of the BDD, or the most important property of the BDD. And I think this is basically the intuitive driving sort of intuition behind this BDD-like structure. We want to compactify to the point where you have just one unique node per partial assignment of our formula, right? So does this make sense to everyone? So do you see that this is a really good thing to have, or do you think that this is, if you're not impressed by this, you'll hopefully be once I discuss some further points, hopefully, right? So are you clear on the fact at least that this entire merging process is basically trying to ensure this property that we have one unique node per partial assignment? Is this clear?
Yes.
By
Yes.
partial assignment, you mean that if you assign values to x1, y1, and x2, the remaining tree we get will be unique.
Right. Or the remaining formula. For example, over here, this formula that we had, so we can, assign partially any number of variables. So in this formula, if you assign some value to x1 and y1, we'll get back a formula, right?
Yeah. Okay.
So we say that in this formula, if we say that x1 and y1 both to be 0, this is the formula that we get back, right? So we just get back this part there. So that's a partial assignment in some sense, right?
Okay.
Yeah. Or we can also think of it as a sub formula, but I don't want to say sub formula because that like makes you think syntactically. This is not some syntactic sub formula that we're looking at. This is a partial assignment, is what I want to say, right? Yeah. So you realize that basically our entire goal behind doing this BDD thing is to make sure that as much as possible, various nodes share various different formulas, right? Like, so basically we don't want two nodes which talk about the same formula being two distinct entities in our memory or in our structure. We want them to merge them together, right? So a BDD does a good job of doing that, but we can do slightly better. And that is basically what it's called a complemented zero BDD. So before I move on to this, are there any questions regarding BDD, or like, do you feel anything about like the merge and the sharing of formulas and unique node per partial assignment? This idea is clear to everyone? Just a yes from everyone would be nice.
Yeah, it's a.
Yeah. Okay.
Yes.
Yeah. Okay. So yeah, so let's look at complemented zero BDDs. And here the motivation is we want to basically, so okay, so before we go to that, let's look at this, right? So here, let's look at y2 and y2 complement. So you see these two trees are also in some sense very similar, like, right? Because we have just flipped 0 and 1. And these two in some sense represent the negations of the same formula, right? And often, in fact, in like if your formula itself is like something based on some decision, often you get this sort of a structure where you get the same, some node representing some complicated formula, and then you have another node representing the not of that complicated formula, the same formula, right? And then what you end up is with basically trees that are isomorphic, but at the end of the day, they just have zeros and ones flipped. Like the leaf nodes are just flipped for these trees, right? So which is the situation that we had here. So it would be nice if we could somehow merge these as well. So in some sense, not just merge nodes which represent the same formula, but somehow also have a node represent both a formula and its complement. So this is basically the idea behind using a complemented zero arc BDD, where we try to merge a node so that basically like merge nodes so that basically they two nodes which only differ in terms of the formula via complement, like which only have some represent some f and some f bar, we want to basically merge them together to one node somehow. And that is the idea in the complemented zero arc BDD. So let's think about how we can do that, right? And let's see if we can come up with the definition of the complemented BDD in some logical step-by-step manner. Of course, I mean, this is somebody came up with it and wrote a paper, so basically it's not very easy, but the idea is basically this. Let's go from the low level upwards, as we have been doing more or less all this while. So at the lowest most level, what we have 0 and 1, right? So we want to merge them together because these are, of course, complements of each other. So we say that, okay, we're going to have only one leaf node, which is going to contain 1. And we're going to add a different kind of zero edge, which is called a complemented zero edge, which will denote the fact that that zero edge leads to a complemented version of the formula wherever we lead to, right? And this will be denoted by a dash with a bubble. So that looks like, that will look something like this. So a dash line and there's a bubble on it, right? So yeah, so basically each node will have either a zero edge, a regular zero edge, this regular zero edge, a complemented zero edge, or just a one edge. There's no complemented one edge. That is basically something redundant that we don't need. We can just do away with only a complemented zero edge, a regular zero edge, and a one edge. And complemented edge means that the function, the node that it leads to, we want to interpret the knotted version of that function. So what we do is basically we are going to merge the zeros and ones at the lowermost level together, right, into just one leaf node. We say that we're going to have just one, and anything that led to 0, we want to somehow mark those edges as being okay. These edges are leading to 0, so these edges are leading to the complemented version of the function being held by this node. So we'll mark them by a bubble, and then we do some sort of manipulations so that we only have 0 edges coming to this negative thing, right? So suppose we had some edges going here and some edges going here. What we could do is we could keep the one edges, or let's use different colors maybe, right? So say we had some blue edges going to the 1 and some green edges going to the 0. What we could do is basically we could keep the blue edges the same going to this new one. And for the green edges, we say that, okay, these green edges are leading to the complemented version of the function being represented by this node. So we are going to mark these edges somehow to denote that fact, right? So that is the idea behind this complemented zero arc BDD. And somehow we can get away with only marking the 0 edge. We can just get away with having one kind of a one edge, not having to mark the one edge at all. By one edge, I mean this solid edge, by the way. So the solid edges are one edge and dotted edges are 0 edges here, right? So, right. And then we'll come to the other points over here. But let's see how we can do this in some cases. So the simplest example is this, where we have, just x and x bar as we had before. And what we'll do is basically we'll have just a single one edge, right? And then what we say is that, okay, we are going to take x, and if x is 1, then we go to 1. So let's look at this one, right? So let's look at this one first. So if x is 1, then we go to 1. If x is 0, then what do we want to do is we want to go to 0, right? But there is no 0 over here. So instead we mark this 0 edge so that, okay, we say that when we go via the marked edge, we are going to treat wherever we land as the opposite of that. So we land at a 1 going via marked edge, and we say that, okay, so now we are going to treat this as a 0 node, right? So that is the idea over here. So similarly, notice that this can actually very easily represent this one as well. And we can do this via this neat trick here, which is instead of routing our tree based on this decision nodes, we augment our tree with another separate sort of boxed root node. And we connect the actual root of a tree via a normal 1 edge or a marked or complemented 0 edge, right? So if we go via the normal edge, then we know that we're leading to the normal version of this function. And if we go by the complemented 1 edge, we use that to denote the fact that we are leading to the complemented version of this function, right? So that is basically the rule here. So we have each BDD is augmented with a root, and depending upon whether we are the function that we have calculated over here ultimately is the complemented version or the uncomplemented version, we either go via the 1 edge or via the marked 0 edge, right? So that is the idea there. And this basically leads to sharing of a lot of variables, and actually can in some cases lead to exponential compactification. I mean, so going from a decision tree to a BDD was itself exponential. Going from a BDD to a 0 arc BDD is also exponential in several cases, right? So one easy rule to basically, so over here, what we had in decision trees and decision diagrams, what we had is that each path, right? Each path that we take from this root node sort of based on the decisions that we're taking, wherever this path went to, that was the final value of the function, right? So if we have x1 is 1, we take 1. If y1 is 1, we take 1. If x2 is 0, we take 0. And if y2 is 0, we take 0. And finally, we end up with 1. So the value of the function there is 1, right? So here, what we need to do is that whenever we pass through a 0 arc, complemented 0 arc, or a complemented 0 edge, we know that the value of the function needs to flip, right? So we again follow the path as we would, but then we flip the value that we get. Like we will always get 1, right? So we read it as 1 if and only if the number of complemented 0 edges in the path is even, right? Because then we have flipped it even number of times, so we should get 1. Otherwise, we read it at odd, right? So for example, here, if you look at this path, when x is 0, if you go down here and you're going down this complemented 0 arc, right? So we have one complemented 0 arc here, and that is an even number of things. So when we have essentially flipped it once, so we take a negation of this 1 and we get 0. So since we have an odd number of not an even, odd number of complemented 0 arcs, we get the final value of the function is 0. Similarly, when we look at coming from this x bar root node, so we have sort of merged these two roots together, but technically they can be thought of as two different trees as well. But if we come from x bar, if you're sort of trying to evaluate x bar, and then we say that x is 0, so we have gone via one complemented 0 edge, and then we go via this other complemented 0 edge, and now we have even number of complemented 0 edges, right? So we flip once, so whatever we get, we're going to take the complement of that now, is what we're tracking. And then when we go via this second complemented 0 edge, we flip again, and whatever we get is the complement of what you were looking at, essentially. So then we basically, since we are basically flipping this one twice, what we get back is a 1. So if they're even number of complement, yeah.
So I have a question here.
Yeah.
So what if we try to change this function f of x is equal to x bar? If we try to make this a complemented 0 or BDD,
Right.
then a straight line will have a 0 on it, right? The straight edge instead of the dot.
Right. So that would be one way of doing it, where you could mark both your 1 edges and 0 edges. But remember that in a complemented 0 or BDD, one thing that we like, one of the small optimizations that are there is that we are only allowed to put a 0, like a complement or a mark on a 0 edge. So you cannot have a straight edge with a mark, right? So we have to somehow come up with a way to represent this function without having to put a mark here. And the way we do that is by augmenting it with a root, like we're saying in this point here. So like I said, what we'll do is basically we'll sort of add a different root here and a separate. Okay, let me go back to black. I think this is becoming a difficult color to read. So if we add a separate root, which actually represents our value of our function, and then we construct our function or its negation depending on what we get, right? So here what we'll see is that what we want is basically 1, and then from x, if we take the one edge, we want to go to 0, right? So we'll complement this function. So we instead make this,
this augmented root is just a dummy variable, right? Or
it's just a dummy. It's just a root, but it has this purpose where the edge connecting you from the augmented root to your actual root can be either a one edge or a complemented 0 edge, right?
So there it doesn't mark any value for x, right? Only when
it doesn't mark any value for x.
Okay.
But what it marks is whether you're taking sort of the complemented version of your function or your original function, right? So in some sense, if you did not have the dummy root, you could only sort of you could only represent x. But having this dummy root lets you say that, okay, this is x, and we're taking the negation of that, correct?
Okay.
Yeah. So this is the sort of way in which you work with complemented 0
Also,
then
when we try to convert large trees, this augmented node can appear anywhere, right? Not only in the root, right?
So in some sense, each augmented root represents one function that you have, right?
Okay.
Yeah. So I mean, it is a matter of decision whether you want to sort of have a separate augmented root for each one of your sub or partial assignments or not. That is like, you can sort of think of that as an implementation detail, right? Because it depends on whether you want to track those functions or not at all, right? So think of this augmented root as only marking whether your root at the topmost level has a negation in it or not.
So can you move to the example that we previously we converted BDD to?
Right. So we want to convert this one to the complemented 0, right? So let's do that. But before we do that, let's actually look at this smaller example maybe first. Is that okay?
Okay.
Yeah.
Could you repeat
so let's do
part? Could you repeat what exactly are those augmentations doing? I didn't follow particularly.
Right. Okay.
Straight edge from the x in the box, which is augmented to the x in the circle. Does that mean it's reading a 1?
Right. So that means that we are not saying that the top level is complemented. So essentially, we can think of the complemented 0 or BDD as having two parts. I think this is like an easy way to think of it. So we have your actual complemented 0 or BDD starting from your like topmost decision node, let's say, and then you have some structure here. And finally, it all goes back into just a 1, right? And then this represents some function, right? So with this augmented node, all that it tracks is that whether it basically allows you to represent the not of this function, because if you sort of like think about it, you cannot represent all functions as just complemented 0 or BDD with no augmentations, but you can represent all functions up to a negation. So this augmented node lets you represent the not of this function. So you can now represent f bar by basically starting with the augmented node and putting arc here. But if you wanted to represent just this f, what you would have done is instead of having an arc here, you just have put a normal solid edge, right? Does that answer your question? Or
sort of. I was a bit confused.
Are you more or less clear now?
Yeah.
Okay. So yeah, so this augmented edge is essentially basically just marking whether we want to track the positive or the negative version of this function. So x is actually a great example, just x, because as you saw, the only thing we can do with just x is this BDD, right? We can have 1 and then complemented 0 edge to 1. This is not a valid COBDD. Let's call this is a COBDD, is a short form for this. So this is not a valid COBDD. For example, we don't allow this, right? And because we don't allow this, since this would have sort of intuitively represented x bar, since we don't allow this, our topmost decision node can never represent x bar, right? So it can only represent x. So in this similar sense, there will be some functions where you won't be able to represent f bar, but you want that. And then the way you get that is by adding this complemented root and then connecting that up with a 0 arc, complemented 0 arc to your x, right?
So the example you did in the picture, The
Which one? The X
no,
one?
no, no. The in the picture we have it on
This
the
one. Yeah, yeah,
slide.
yeah. Yeah, yeah.
So we have an augmented node of X, right, in the top.
Yeah, yeah.
No, that's not necessary, right?
Yeah, so the augmented node of X is not necessary in the sense that because we have already can just
Yeah,
have
yeah, yeah.
just
Okay.
this, right? Yeah, but we keep it just for consistency's sake, you know. In some sense, we like, I mean, since we need an augmented node anyway, oftentimes it makes sense, like
Okay.
it like
COBDD needs to have always an augmented node.
always an augmented node. Like we make that a part of the definition. And I mean, you could sort of modify the definition slightly and get away with not having an augmented node when you're not dealing with the negative version. That is fine. But you know, then you'll have to always case split based on whether you have an augmented node or not, right?
Okay.
So that makes your like both your reasoning and your code potentially messy. So that's why we just keep the augmented node always and just either have a straight edge or a like negated one, that's zero edge.
Okay.
And that is, I think that is like a slightly more elegant than having or not having an augmented node being um, the decision basically. Does that make sense?
Yeah, yeah. Okay.
Yeah. Okay. So yeah, so let's look at these examples as well. So again, we have two functions. These are more complicated functions, x and y bar, or x bar plus y. But notice that again, they are complements of each other. And if you look at the BDDs, again, you see that only the zeros and ones are being flipped, right? So let's see how we would convert this into a complemented zero arc BDD, right? So again, you would merge, like, or let's say that you would only have one over here, right? So here okay, since I have this on the slide, there's no point drawing it again, I guess. So here we have just one, right? And then right, so and then you have based on your x's, like your actual so your topmost thing is basically just a y, right? So y sends a solid edge to 1 or a dotted edge to 0, or in the knotted version sends a solid edge to 0 and dotted edge to 1. So remember that the only thing we can do here is send a solid edge to 1 and complemented dotted edge to 0, right? So this is the version that we can only, this is the only version that we can represent in the COBDD structure, right? So we decide on y, and we say that okay, we are going to basically represent y over here instead of the y bar that we had over here, right? So we represent y over here, take the solid edge and the complemented dotted edge. And so this represents your y. So it says that, okay, if y is 1, then go to 1. Otherwise, go via the 0 edge complement ones to go to the complement of 1, which is 0. And now we have over here x, right? So x, in our case, would basically send a solid edge to the y and a dotted edge to 1, right? So we send a solid edge to y and dotted edge to 1. So now this essentially represents, if you notice, x bar plus y, right? At this point. So if you wanted to represent this one, you would have to put a dotted zero arc edge. Or if you wanted to represent this one, you could just put a single solid edge, and you have both of those two things being represented by this same structure. So in fact, if you're working with like just this, like if you had multiple copies of this formula as partial assignments in a much larger formula, then you would have gotten away with just one structure instead of these two copies. And that is the benefit of the COBDD. So let's move on to like a slightly more complicated example. And we are sort of running out of time. I think it's already 6:40. I wanted to cover quite a bit more than this, but let's see however far we can go. So right. So let's try to convert this into a COBDD, right? So basically, I'm going to use this one method to do it bottom up. This is, I don't claim this to be a very like complete and robust formal algorithm. You can maybe hopefully get an intuitive idea of what the algorithm should be, and then that could be an exercise maybe. So we just have one, right? And now we have two y2s over here. Let's again mark them as blue and green as we had previously, right? And let's see what happens for these two y2s. So we have green and blue So let's start with the easier one, let's say, right? So we have the y2 that sends a solid edge to 1. So that's the blue y2. So let's do the blue y2 first. So we have the blue y2, and this sends a solid edge to 1. And so basically it says that if y2 is true, then we go to 1. If y2 is false, we go to 0. So that becomes, we take a complemented 0 arc to 1, right? So above that, we have the x2, and the x2 sends a solid arc to y2, correct? Now let's look at the green y2. The green y2 does the opposite of the blue y2, right? If it is a solid edge, it sends to 0. And if it is the complemented, like if it is 0, then we go to 1, right? So what we would want to do is something like this: a green y2 sending a complemented solid edge to 1 and a dotted edge to 1 again. But as I said, this is not like allowed in our C2C or BDD structure. Instead, what we do is we notice the fact that this y2 is basically just a complement of this y2, right? So when we're going to this y2 from the x2 via this dotted edge, instead we take a complemented dotted edge, right? So previously what we were doing was, if x2 is 0, then go to green y2. Instead, we now recognize that what we're doing essentially is, if x2 is 0, then go to complement of blue y2, right? Because green y2 is just the complement of blue y2, correct? So basically, so we put a complemented dotted edge from x2 to blue y2. One way to maybe think of it as an algorithm is that we do construct this green y2 as this green y2, and then we realize that we can't put a solid edge. So a solid edge to 0 convert corresponds to a dotted edge to 1 corresponds to just a single dotted edge to 1. But a solid edge to 0 basically means that, okay, we can't do that. So we have to put a solid edge to 1, complement here, and then have a complement over here, right? So we basically mark this as being a complement of this. And then whatever edges come in from over here, we mark those as being complemented over here, right? So this is sort of a rough sketch of how you could do it algorithmically, but I'm not going to go into too much details about that here. But basically, you can sort of add complemented solid edges and keep removing them bottom up, right? So we have this structure done up until x2. So now let's look at y1. So again, we have y1, and let's say that this is the left y1, right? Or the okay. So we've been using blue. So let's start with the right y1, right? And so we have a solid edge to x2, and we have a dotted edge to 0, correct? And then above that, we had an x1, which sends a solid edge to this y1, right? And now this
dotted edge will have a bubble, right? From y1.
Yeah. So this will be a complemented dotted edge. So this above x1, which sends a solid edge to this blue y1, it has a dotted edge to a green y1 here, right? But again, if you look at this green y1, I mean, if you were to sort of construct it, what this green y1 does is essentially, so if we have a green y1 here, we see that this green y1 sends a dotted edge to x2 and a complemented solid edge to 1, right? So we basically mark this green y1 as the opposite of that. So we since we have a complemented solid edge in the green y1, we remove the complement, put the complement in the dotted edge, and mark this green y1 node as being complemented. And then we know we can sort of put a complement in this 0 arc from the x1 leading to the y1, right? So what we end up is basically with the same copy of the green y1 and blue y1 ends up becoming the same copy. And we can remove this redundancy and put this dotted complemented arc to y1 here instead. And we don't need any of these edges anymore, right? So this is your final complemented PDD for this. And as you can see, this is much more compact. Like there's only one node per variable. It's just some links. That's it. So is the sort of the definition and the idea behind complemented zero BDD clear?
Yeah.
Yes.
Okay. So one thing that I just want to note, like want you guys to notice, is that this limitation that I mean, I don't know if you feel this way, but at least I felt it this way when I saw it. Why not have a zero edge, like a complement of the one edge, right? The thing is, then you lose the fact that you like in a complemented zero BDD, you actually have the guarantee that f and f bar will always share the same node. This guarantee will not hold if you allow complements on the one edge, because then then we could have had, for example, over here this y1 here with this complement and this dot going like this, and then you could have put in that dotted edge over here, right? This, if we had allowed a complement on the one edge, this would have been an allowed complemented zero BDD, but then we have the function and its negation not being shared by the same node. So since we want to avoid that, that's why, like, one of the ways we enforce that is by basically not allowing the complements on the one edge. So if we allow complements on the one, is this guarantee that f and f tilde will be shared by the same node is not going to be valid anymore.
Can everything be expressed with if we disallow complemented one edge? Because suppose there was a solid edge from y1 to y2, then
Right.
wouldn't we need to have y1 to the left y2? I mean, then the green one. Then wouldn't we need to have a complemented one edge from y1 to the blue y2?
Right. So your COBDD structure, like your normal BDD structure, is y1 solid edge to green y2, right?
To green y2, yes.
Yeah. And you don't have this one. So you don't have this edge at all. Okay. This edge is not there, right?
Yes. So wouldn't we need to then include a complemented one edge to the blue y2, because the blue y2 is computing the complement of the green one?
Right. But then so this solid edge, you're saying, basically would end up going to this blue y2. But because you're taking a complement, you would have put a complement on this edge, right? But then what you would have done is you would have sort of flipped that around and taken a solid edge over here. So let's try and do this. Let's see what this gives us, right? So up until y2, everything should be fine. And I think up until x2 as well, everything should be fine, right? So we have done the blue y1. Let's forget about the x1 above for now. And let's try and do this, right? So we have this this new y1. Let's say this is the green y1. And so let's first make this green y1 normally, and we have this dotted edge to x2, and we have a solid edge going to a green y2. But since this green y2 is like the blue y2 is a complement of the green y2, we need a complemented solid edge over here, right? So now what you can do is, again, you can flip this and say that, okay, what we're doing is basically, if y1 is true, then take the complement of y2, or if it's false, then take the complement of take x2, right? So instead, what we can say is that if y1 is, if not y1 is true, then also, okay, so then also we'll need this complement of this one, right? So essentially, then also, so okay, let's try this. So if you have y1 is false, then when we go through the zero edge, we will end up in x2, and if y1 is true, then we need to end up in not of y2, right? So if not y1 is, so if we look at the negation of this function, right? So if we want to look at the negation of this function, what we want to say is, if y1 is false, then you want to end up, okay, yeah, so let's look at this. So let's negate this function over here. So this represents some function f, but what would represent f tilde? Sorry. So f tilde would be represented by this, right? So if your y1 is true, then you would have gone to the negation of blue y2. That is your f, right? But in f tilde, you would have gone to just blue y2, correct? Do you follow me here?
Yes.
Up until this? Yeah. So if your f again decides based on y1, if y1 is false, then it goes to x2, then your f tilde would basically go to complement of x2, right? Right? Hello?
Yeah.
Yeah. So now you basically have, instead of representing your green y1, you have represented the complemented of your green y1 node, right?
Yes.
Yeah. So now your
Hi,
previous
Digant, I'm
situation.
back.
Yeah. Hi, sir. Yeah.
Okay, go ahead.
Yeah. So I'm sorry. We are still discussing this BDD, and we have moved into the complemented zero BDD.
Oh, no,
Yeah.
no, go ahead. No, not a problem.
Yeah. Right. So okay. So now you have this situation where you, instead of having to represent this y1, just y1 as a node itself, you have represented the complement of y1. Like if y1 was f, you have represented f tilde, right? And then what you can do is, from x1 you had solid edge to this blue y1, and you had a dotted edge to green y1, right? So instead, you don't really have this f node over here. So what you have in this COBDD structure is this f tilde node. So instead of taking this dotted edge to your blue y1, you take a dotted edge to your f tilde, and you complement that, right? So then what your final thing becomes is that if x1 is false, then instead of taking f, you take complement of f tilde, which you have represented.
I
So
understand this example,
yeah.
but I have one question. Like, would this process always work? Like, basically, we are propagating the what we have as one black edge with a complement. We are propagating that upwards. That's what's happening.
That is
What
exactly
if,
what's happening, right?
but what if x1 to green y1 had a
Hmm.
solid edge?
X1 to green y1, right?
Yeah.
So
Instead
so
of a
then you,
dotted edge.
right. So then what you have is basically this situation, right? So let's flip this x1. So you'd have something like this. So then maybe, okay, so
Okay,
let me
so
just erase this.
we can still use the same tree and we can have an augmented root, which
Right,
takes the
exactly. That's where
complement.
exactly the augmented root will come in. So then you have essentially ended up representing the complement of your function. So if this was your situation, right? You're saying?
Okay, I understood it. Got it.
Yeah. So then you have ended up representing the complement of your function, then you take an augmented root out. So essentially the process can be sort of formalized in this way. Like you allow complemented edge for a while, like complemented one edge for a while maybe, and then when you have represented something like that, you flip that, so you ended up representing the complement of that, and then you complement the incoming edges, and then you keep moving this upwards. Finally you'll reach your root, at which point you'll have to like you'll have your augmented root, and you'll either have to take a one edge here or a complemented zero edge here, depending upon whether you want to finally push the complement up or not. So does that make sense?
Yeah, and just to confirm, the reason we disallow solid one complemented edges is because we want the representation of each tree to be unique.
Exactly, yeah. So not just unique, in some sense. So even if you, yeah, so even if you did not disallow this complemented zero edge, sorry, one edge, you would not just lose uniqueness, you'd also lose this crucial fact that is reduce, like causes this exponential reduction in size for COBDDs, which is that f and f tilde will always need to be shared by this node. So if you allowed complemented one edges, not only would you lose your uniqueness, and you wouldn't really be able to call this a canonical normal form, but also you would basically end up in a situation where you can have sort of the complement of two nodes existing within your COBDD structure, which you don't want, which is the entire point of going to a COBDD from a normal BDD, where you want to sort of capture both the complements of your partial assignments in the same node, right? So there are two reasons why you want to disallow this. So okay, maybe I should write it somewhere here where there's some empty space. Yeah, so there are two reasons why you should want to disallow this. So one is you want to disallow this because uniqueness is lost, and the second reason is you want to merge nodes for f and f tilde, right? So disallow complemented one edge because yeah, so this is the idea. So I think I'm probably out of time right now. I've got 2 minutes. Does anyone have any questions?
So what do you need to cover? I guess did you also cover operations on?
No, I did. No, I couldn't go into any of those things. I just introduced BDD and then this spent some time on the complementary.
Should be fine. Okay, so I think next you can take half of next class, maybe, or maybe it's less than that, to half of next class to finish the theoretical part. Okay,
right.
And then the remaining half to show them how to use CUDDD package. Now maybe that they can do some homework. If you provided the material, I mean, I think I have the material for CUDDD, the reference manual, and how to implement and so on, that I will upload, okay? By the way, you should ask them the question. This is the right time. So what language do you prefer to do?
Right.
Yeah, can you?
So what is the, like, so CUDD as a package itself is the native interface is in C. So is everyone like familiar with C and some basic like memory management related pitfalls you can have there? Because otherwise I think we'll have to move to some other language. So is there anyone who is like, is everyone familiar with those things or not? It's just, yeah. Hello?
Yeah, I'm familiar with C. I'm okay.
Okay. Is everyone else? Because everyone needs to be familiar. If there is even one person who is not, then we'll move to some other like binding for CUDD.
What memory management pitfalls in particular are you referring to?
So you'll have to, so you'll have to basically CUDD package asks the user to do some reference countings of the node. So you just have to make sure that you remember to do that and you don't end up reference count, like increasing the reference count of the same node twice and things like that. I mean,
yeah, okay.
Yeah. So is everyone okay with this?
I think I'll be okay. Like I usually code in C++. So
yeah. So that should also be okay. So I'll in fact, if everyone prefers it, I can show you some C++ code for this as well, because then you can wrap this sort of reference counting in your constructors and destructors, which is like a safe and nice and safe way to do it. So okay, I mean, yeah. So that is one idea for people who are more versed with C++ and C. So okay, so if it is fine with everyone, then I'll use C and C++ maybe itself. Is that okay?
Yeah, it's okay.
Okay. So yeah. So okay. Yeah. Right. So yeah. So this is it. So now, do you guys have any questions on BDDs or COBDDs? Or otherwise, we can, I think, maybe end the class.
Could you repeat the second point that you just wrote here? Like
this one?
Yeah. What is happening here? I think I missed that part.
Right. So essentially, let's look at this one, this green Y1, blue Y1 sort of example again, right? I'm sorry, I'm probably going beyond 7 right now, but let's,
okay.
I think
once you lose uniqueness, then what's the use? No, so that is, I mean, the point one itself is.
Yeah, so this is a very important point in itself, because uniqueness is a very important thing. But yeah, so another thing, like basically what I was also saying in point 2 was basically just that you should not have this situation in your previous example. So let's maybe duplicate this slide and erase everything here. So in the
one point that I had was, if you allowed the complemented only for one, then I think you're okay. Okay.
Yeah, definitely.
You can't allow it for both.
Right. Exactly. That is exactly the issue here. So basically, if you allow it for both, then you can just, like, whenever you want to take like, for example, in this case, you can just do something like this, right? So or even for Y and Y complement, you could just do something like this, right? So you just put Y as this, and then you just put Y complement as this. But this entirely defeats the point of sharing the y and y complement nodes, right? Because not only is this not unique, because as I said, if you allow your like augmented nodes, you can have different representations, but also this basically like means that y and y complement can live in two different nodes, which is something you don't want, which is something you want your constraints on your COBDD structure to like make this situation an impossibility is what you would look for. So that's what I'm saying over here. Is this clear?
Okay.
Yeah. So anything else? Any other questions?
Like, is it the case that for all COBDD, there will be only a single node for the corresponding variable?
No. So in fact, I think right here we see that that's not the case, right? So by a single node, you mean just one decision node for each variable, right? So this is an example of a COBDD where that didn't happen, right? So okay, for this structure, we came up with this COBDD where we had two y1 nodes, right?
Yes.
Yeah. So that is not true. I mean, this example was actually chosen so that this example was chosen so that things become nice. Basically, this example here was chosen so that COBDD turns out to be nice. But yeah, in general, that is not true. But there is like very often there's an exponential reduction in the number of nodes. Okay. Because at each level things can sort of half. So yeah. So any other questions?
What is the PDF viewer you are using?
Okay, yeah. So this is Zernal++, but yeah, I think we can maybe, okay. So I don't know if people have time constraints after this. So yeah, so this is Zernal++, which is, I'll send a link for this, I think. Yeah, this is really nice. This is a PDF. Yeah, I'll send this to everyone.
This something like this, because without that, I spend too much time trying to draw pictures ahead of time, taking pictures and so on. So
yeah, this is really useful for these kind of situations. Like you can just leave some space for pictures in your slides and then yeah. So
I think it's also useful for students to ask questions by drawing things. Huh?
Yeah. Then you can draw this particular example out and explain that way.
But you are good at. I mean, usually you guys, the old people like me are not as good, as adept at using.
No, this actually like I mean so even my mother, she also teaches, so she also switched to this, and it was just like 2 days she took to like write something down, and she got completely versatile with this. This is very easy to use.
Okay, so that's I'll try to.
Yeah. This is really nice, actually. I'll send a link for all of these things. Like the important thing I think is to have like this hardware tablet, because then you can just, your muscle memory for writing comes into use. You don't have to use your mouse, which is I think difficult. But other than that,
a tablet, huh?
Yeah. So you can use this with a mouse, but then drawing with a mouse is basically really difficult. It looks like this.
Oh, I thought you were drawing with a mouse.
I see.
Oh, that's
no. I'm drawing with a tablet. Yeah.
So a tablet with a pen. I don't have one. That's the problem.
Yeah. Okay. Yeah.
So I have a question. So binary decision diagrams, and these are all. It is good for Boolean formulas or proportional formulas, right? But in model checking, we will have like a variable can have real values and all, right?
Right. So there also you can have some similar structures, but these BDDs are these really nice properties of BDDs work very well for Boolean formulas precisely.
Let me interject there. So why do you say, okay, first of all, finite state model checking, if you just stick to finite state systems, you can always reduce to propositional logic. Okay, was that Paramala who asked it?
Yes.
Yeah. So I keep insisting on this. Okay, so finite state systems, you can always encode the states as using if there are n states in a universe, use log n bits. Okay.
Okay. Okay.
So you can reduce it to propositional logic. When do you need to work with other data types? I mean, you're right that you can do model checking in infinite state systems. Okay. Or infinite state systems, you can extend these model checking. Then there is something satisfiability over theories. Okay. Over combination of theories, and the theories could be real, integer, and so on. Then you're getting into the satisfiability problem is not decidable, or it's decidable only for some fragments, like for example linear arithmetic and a few data types. You can combine them with that. Linear real, the satisfiability problem is decidable, linear programming. Okay. So then you can combine them with Boolean logic and other data types for which there are decidable theories, and you can come up with something called, and that's what SMT is, and Z3 is actually an SMT, as Diganta showed you. Okay, with as long as you restrict yourself to the decidable fragment of those theories. Now the model checking problem is still not decidable. May not be decidable because the reachability problem, even if you restrict yourself to linear fragments, etc. I mean, when you take existential quantification, which is what you need to do, then it may not be decidable. Okay. So as long as you're willing to sacrifice decidability, you could still do it. I don't know if that answers your question. Okay. So I mean, I guess my answer gave more than what you asked. I mean, your question was.
So yeah, but in the algorithms for explicit state model checking, every algorithm has an upper bound, right? Like it has a linear time, right?
No. Wait a minute. I'm saying that once you extend this to infinite data types, it is even undecidable. There's no question of upper bound. Okay. So the reachability problem becomes undecidable. What I'm saying is, even with those data types, there might be your transition system and relation might be such that you could make it if your reachable set somehow can be. I mean, it can be reachable in certain situations. Okay, that's all I'm saying. Okay, so what do you mean the upper limit? That part I did not understand. So within the decidable fragment, you're saying upper limit?
Yeah, I mean every algorithm has an upper bound of, like the algorithm for EG has an upper bound of order of S plus T, right?
No. So assuming it is, suppose restrict yourself to finite state systems, let's say proposition logic or some things that can be encoded. Okay. Now you know that Boolean satisfiability is NP complete. Therefore, your bound and model checking is p-space complete on finite state systems. Yes, so there is an upper bound which can be exponential. Okay, time exponential. So yeah, so there is an upper bound. So what is the point? Yeah, the worst case complexity.
So what I'm trying to say is, we saw an algorithm which runs in linear time, right? So that means for every input, it will stop after a finite time.
I'm going to say that again. I know for some reason recording stopped, but so I'll stop live stream. I don't know why recording stopped.
I think Diganta left.
Diganta left. Okay. No, go ahead. Yeah.
So what I'm saying was, we saw algorithms for explicit state model checking. Right?
Correct. Yeah.
We gave upper bound to every algorithm, which is kind of linear to the number of states, right?
Yeah, that's fine. Yes.
But I think the problem is because of the state explosion, right? The number of states can be exponential. Therefore, the algorithm will also run for exponential time.
Correct.
Okay, okay. That's when it becomes undecidable, right?
No. Then undecidability is a separate issue. Okay, if it is undecidable,
okay,
there's no
yeah.
question of bound. Okay.
Okay. I get it.
If the problem is undecidable, there's no question of there being a bound at all. No? I mean, the bound comes only if it is decidable. So the boundness you can talk about in a decidable context. Yeah.
Yeah, okay.